All right. Had to pause my music there. Sorry. Uh, we'll continue on here. There is a concept that you will encounter sometimes, and I notice sometimes people will use these, probably just blindly copying them from some solution service or maybe AI at this point. They'll use these equations, very powerful equations, wonderful tools. I call them the K ratios. And just like any other tool, they have their time and their place. Let's talk about where these come from. So again, we'll do a quick derivation and see how these come about, and so we have a better understanding of when and how we can use them. So the what we call the K ratios, what are these? Well, if we start with the Gibbs equation, right? And specifically, and again, I double F, and I always ask a class whenever I write that on the board, what does this mean? Most people will say, well, it's if and only if. Yeah, if and only if you have isentropic and ideal gas. So you have to have two things here. And remember, two things tell us it's isentropic. It's not just adiabatic and it's not just reversible. If I have both adiabatic and reversible, that means it's isentropic. That comes from the second law. We've done that a few times. And it's an ideal gas. We have these two things, then we can use Gibbs equation, right? Where Gibbs equation says delta S, which if it's isentropic, delta S is zero. And delta S is approximately equal to, you can start with any of them. We'll use the constant specific heats, and let's do this one. C sub P at the average temperature times the natural log T2 over T1 minus R ln P2 over P1. Right? You can start with any of them. We could also do, of course, there's this, or you could also do 0 is approximately equal to C sub V at the average temperature times the natural log of T2 over T1. And this one is plus R ln. And this one has the ratio of specific volumes, little v2 to little v1. And maybe, you know what, let's derive from this one. Let's start with this one. Okay. So if we take this one, both are true if it's isentropic and an ideal gas. There's a further simplification we can do. It's very, very powerful. So here's what we can do. If we take this one, and I'm going to move this R ln ratio of V's to the other side, so it's going to pick up a negative sign. So it's going to be C sub V average ln T2 over T1 is approximately a minus R ln little v2 over little v1. And if you remember some logarithmic algebra, I can distribute this negative sign because means the natural log of v2 minus the natural log of v1. Well, if I distribute the negative sign, then what happens is it just flips. This becomes R ln specific volume 1 over specific volume 2. It just flips the ratio. Right? That's a logarithmic rule. You distribute the negative sign, and it flips the ratio inside the logarithmic argument. Now, here's what I'm going to do on the next line. I'm going to stop writing approximately. I'm just going to call it equal to. And I'm also going to stop writing average after the C sub V, after the specific heat. And we're just going to understand that we're talking about an average specific heat. So here's what I'm going to do. I'm going to say that the natural log of T2 over T1, I'm going to write equal, but again, we'll acknowledge that it's still approximately. I'm going to write R over C sub V, and we're going to acknowledge that this is C sub V average times the natural log of V1 over V2. Okay. And then we're going to recall some logarithmic algebra here. And if you're like me, you may not remember it anyway. And so you're just going to brush it off or go look at some service like Khan Academy or something like this, go watch some videos and remind ourselves that if I have x times the natural log of y, that is the same as the natural log of y to the power x. These are the same. Well, here I've got r times the natural log of something. This is basically x times the natural log of y. And so what I can do is I can say, well, this is the same. This natural log T2 over T1 is equal to, and again, I'm just going to push this inside. This becomes the natural log of the ratio V1 over V2, and this is going to get raised to the power of R over C sub V. Okay, simple enough. Well, simple is a relative term. We're still doing logarithms, which for some reason everybody still doesn't like. I get it. I didn't really like. Well, I should be honest. I hated logarithms. If I'm being honest, I hated logarithms until honestly until I taught college algebra a time or two, and then it's like, oh, it's actually they're actually really simple. But that's another video for another time. And I'm sure you can find some people that teach math for a living that have actually put out really good logarithmic basic explanation videos. At this point, if you went back and watched them, you'd probably be, oh, that's really not that hard. They're really not that complicated. I digress. Another thing to recall, also recall. Now, we talked about this, I think, in chapter 4, and I think in chapter 4, I probably said something like, we're going to mention this, and you probably won't see this again or even worry about it again until chapter 7. Well, here we are right in the middle of chapter 7. In chapter 4, we said that C sub P is always larger than C sub V, and the difference between the two is the R value, the gas constant for our specific gas. The universal gas constant divided by the molar mass, that's this R value. The difference between C sub P and C sub V is this R value. And also we have this K value. The K value is the ratio of C sub P to C sub V. So if I take these two and I combine these and I say, well, if I've got R over C sub V, which is what I have here, R over C sub V then equals, you got C sub P minus C sub P over C sub P. This is K, and this is 1. This becomes K minus 1. Now, another thing to mention as we go through this derivation here, this one's hopefully a little more obvious. That's not too complicated so far. If I add one more thing to this, another lecture 20 page, note that also the natural log of x, if the natural log of x is equal to the natural log of y, if the arguments for the same function are, if I've got natural log of x is equal to the natural log of y, if I'm using the same function and it's equal to each other, then the arguments must be equal to each other. That means x must equal to y. Right? And it's actually, well, an arrow's fine, with an equal sign also works. Yeah, if these two are equal, then the arguments had to be equal. So notice what I've got up here. I'm saying that I'm taking the natural log of a thing, x, and this is the natural log of another thing, y. And since they're both equal, that just means that x must equal y. And so we're going to employ that logic there. So what that means is I've got this ratio, T2 over T1 now is equal to the ratio of V1 over V2 if this ratio is raised to its to the power of R over C sub V, which we've derived down to K minus 1. So this is to the power of K minus 1. This is the first of what I like to call the K ratios. The K ratios. And in the Shangle and Bowles text, if you go to the chapter 7 summary, here are the K ratios. And you can find these if you look up isentropic ideal gas isentropic ratios. You'll get these. I'm going to see if I can focus this. That's better. I'm further up. This is on top of my paper, so the focal length changed. So notice, and this is the one we just derived. T2 over T1 is equal to V1 over V2 to the K minus 1. There are other ones, right? We mentioned earlier, you've got these other equations, right? You've got this other equation, this one. You could go through a similar derivation, and you would end up with this this one here, right? And then the ratio of pressures is equal to the inverse ratio of specific volumes, simply to the power K, the specific heat ratio, right? So those equations are available to you. And again, there's a couple of rules that you have to follow to use those equations. If it's isentropic, and I'm going to share screen. I'm going to switch to my PowerPoint slides because we're going to write these out. So the K ratios simply say that the one we just derived, right? Oh, apologize. T2 over T1 is equal to the ratio of V1 over V2. This one is to the K minus 1. You got another one that says T2 over T1 is equal to the ratio of pressures P2 over P1. This one is the power of K minus 1 over K. And then finally, the ratio of pressures P2 over P1 is equal to the inverse ratio of specific volumes, V1 over V2. And this is simply to the power K. In all cases, the K value is from the same table you would go to look up C sub P and C sub V values. You would get K values. The K value, but a few things to notice here. All right, let's write the rules. Rules must be isentropic. How do we know it's isentropic? We look at the second law, and the second law tells us that if it's adiabatic and it's reversible, then it's isentropic. Must be isentropic. Must be an ideal gas. Don't use this for R134 ever. Be very careful using it for water. I would recommend against it. You'd have to know the water is in the vapor phase, high vapor phase for both. And even then, it's only an estimate. You have property tables that give you the S values and all these other properties. I don't see any reason you'd use this for water. If you know it's water vapor, you might could. Any refrigerant, you run the risk of it becoming saturated or even a mixture, and now it becomes a garbage estimate, okay? But if it's something like air, nitrogen, or anything else that's in the gaseous form, these are fine. Last one. Recall that your K value that I've listed there is actually equal to the average K. What do I mean by that? Remember back here, I said, hey, I'm going to write C sub V at the average as approximately equal to this. And then on the next line, I said, hey, I'm going to quit writing approximately, and I'm going to quit writing C sub V average. But I want you to remember, this is referring to C sub P average. So we're referring, and because then eventually we got down here and we said, well, instead of C sub V, now it's going to become K. This was a C sub V average, meaning the C sub P is also an average, meaning their ratio to K is also an average. K is a function of temperature. It will change as temperature changes. It doesn't change nearly as much as C sub P and C sub V do. So it's actually even more constant than those are. But it still changes as temperature changes. So you're going to have to use a good average value. So I normally like to go back through that last problem and look at it quickly and say, hey, if we apply one of these to that last problem, right? So remember that so I'm going to stop sharing screen here. So remember the last problem. You go back and look at the examples we've been working for lecture 20 with that's the nozzle with I think it's air. T2 is equal to T1. Well, let's do this. Let's start with the ratio. T2 over T1 is equal to the ratio of P2 over P1. And this one is K minus 1 over K. Now that is a situation, that last problem is a situation we have an ideal gas and it's isentropic. So this equation works. And so we were looking for T2. So I'm going to solve here for T2. So T2 is equal to T1. times, this video will be a little longer than 15 minutes, and that's okay, times P2 over P1 to the power of K minus 1 over K. Now, again, what I'm saying is these are K averages. These are K averages. K average minus 1 over K average. So we're still going to need to use a guess and check on that last problem. I didn't know T2, meaning I don't know the T average. So I'm still going to have to guess T2, and using T2, that's going to give me T average. T2 and T1 together are going to give me T average. That's going to give me a K average, which then is going to give me a better guess at T2. And I'm going to repeat until I get the same value over and over again. Right? And so if I do this quickly here, so we're going to have, if T1 is equal to, we said 540 degrees Fahrenheit, so if we're going to guess, well, let's just do this rather than do that. So this is the neat thing about these. If you go look at the table, notice that for just about any temperature for air, K is 1.4, right? It's going to round to 1.4. So what you could do is you could just guess in that last problem we had. If we guess K average is about 1.4 for air, it's a good starting place. So basically I'm going to start here in the loop. That's going to say, all right, well, that means T2 is equal to T1, which is 1,000 Rankins, multiplied by the ratio of pressures. It was like 12 over 60, both those PSI. And this is K average minus 1. So I'm going to say 1.4 minus 1 divided by 1.4. So we're going to have, I'm going to do the exponent first. That's going to be 0.4. It's 1.4 minus 1 divided by 1.4. That's my exponent. I'm going to use that exponent then and raise to the power of, let's see, we're just going to do it, 12 divided by 60. Could probably do that. I was going to say, I think that's 0.2, right? So that's 0.2 raised to that power. And we'll multiply that by 1,000. And then we'll minus 460 off of that. That doesn't seem right. I'm going to pause and let me double check my numbers. Okay, I think I figured it out. I put it in my calculator wrong. I put it in my calculator wrong. It's going to be, we need to do the ratio first. 12 divided by 60. I can make mistakes too, and you know, sometimes you can catch it and sometimes you don't. But if you show me, in the lesson here is if you show me this and then you give me the wrong answer down the next line, I'm like, well, this is right. You just made a calculator error and you're going to get most of the points. So we'll do this first. We'll actually use the calculator correctly. So it's going to get raised to the power then of the exponent. So now we calculate the exponents. 0.4 divided by 1.4. And we'll calculate that out. And then we multiply that by 1,000, and that looks more realistic. So that tells us a good guess for T2 would be about 631 Rankine minus 460 gets us down to T2 is also equal to 171 degrees Fahrenheit. So then we say, all right, well, if T2 is in fact this 171 degrees Fahrenheit, so we go through the loop now. Now I've got a good guess for T2. And since T1 is 540 degrees Fahrenheit, we're going to average those two. So plus 540 divided by 2, that's giving me about 3. So that means T average is about, you see it here, about 355, 356 degrees Fahrenheit. So that means K average, a better guess for K average. So 1.4 was an okay guess for K average. Let's get a better guess for K average. So a better guess would be where T average is about 355, we'll say about 350. So it looks like K is going to be between 1.394 and 1.389. So I'm just going to go halfway in between those. That's 5 in between. So 5 to this one, 2.5. Looks like K average is going to be 1.3915. Let's use that. And so now we recalculate T2 with that. So I've got 0.2 as my ratio of pressures. That's going to get raised to the power of 0.3915 divided by, no, I did that wrong. 0.2 raised to the power of, parenthesis, 0.3915 divided by 1.3915, close parentheses, compute, multiply by 1,000, and we get almost the same temperature. Tells me T2 is about 636 Rankine, which is exactly what we got last time, I think. Yeah, and so if you go back through, it's about 100 and right about 170 something Fahrenheit. You go through, you'll get another T average about the same, another K average will be about the same, and you'll just repeat through. So this ends up being the correct answer for T2. That gives you then T average. You could use C sub P average, or you could go look up an H value from that number. So a third way to do this problem, this one does require guess and check, but because the K average value is very stable, you can pretty much just put a rough guess in for K average first. That gives you a very good average or value for T2. Run it one more time through the loop, and that's going to be about as good of a value as you're going to get. Okay. And that's something that's going to get lost if you are just looking at solutions manuals or just letting AI do this for you. You're not going to get the subtlety of, no, they actually should be doing guess and check. They're probably just making a really good first guess and not going through the loop again. And I'm going to count points off if you don't show me that you verified you're in fact using a good value for K average. Okay. Hopefully that makes sense. Let me know, send me an email or let me know in the comments, whatever questions you have. We'll go from there. All right, guys, hang in there.